physics. It's everywhere. It's all around us, from falling balls to crumbled paper. And all we need to do is look for it. But what if we can't look for it? What if it's too small for us to see? And that is why we have quantum physics. The first major discovery of quantum physics happened when J.J. Thomson constructed a cathode ray, a glass tube which is partially evacuated and applied high voltage between two electrodes. Through these experiments, researchers noticed that objects placed in the tube in front of the cathode could cast a shadow on the glowing wall, and realized that something must be traveling in straight lines from the cathode, which made the conclusion that light has to travel through a medium. Thus, it is realized that light can be considered a wave. Blackbody. A blackbody is a body that can absorb all radiation falling into it, and at first theorized, it emits infinite radiation according to classical physics. But because of the discovery that light is a wave, Planck theorized that energy emitted from the blackbody is in limited amounts and not at all infinite, which led to his hypothesis. Planck proposed that the energy of any harmonic oscillator, such as the atoms of a blackbody radiator, are restricted to certain values, each of which is an integral multiple of basic or minimum volume. Therefore, Planck came up with the idea that light energy can be only emitted and absorbed in discrete bundles called quanta. This hypothesis gave Einstein the idea that oscillating waves is finite and not continuous, and therefore oscillating waves have a particle nature. This theory is then proven by experimenting on metal. When you shine light of enough frequency onto a metal, electrons will be emitted from the metal. It happens because electrons can gain energy by interacting with photon or light. Once electrons have enough energy, it will escape the metal surface. Another experiment that proved that light was a wave and a particle was Thomas Young's experiment. His experiment uses light to pass through two slits that interfere, and the wave nature of the light causes the light waves passing through the two slits, producing bright and dark bands on the screen, a result that would not be expected if light is considered a particle. However, the light is always found to be absorbed at the screen at the discrete points as individual particles, thus proving light is both wave and a particle. Wave and particle duality. The revelations of quantum physics and the theory of light sparked an update to the atom model. Previously, the Rutherford model uses classical physics law, and electromagnetic theory was still unstable. This is due to the fact that charged particle moved on a curved path would emit electromagnetic radiation that would lose energy and spiral into the nucleus. After all the research that has been done on quantum physics, de Broglie proposes that electrons and other particles of matter behave like waves. According to the hypothesis, massless photon and enormous particles must satisfy one common set of relations regarding energy with frequency and the linear momentum with wavelength. This is important because it was a fundamental principle that it exhibited by both radiation and matter that would be crucial in quantum mechanics.